All right, guys. The holidays are coming to an end, and you guys have got your physics paper three GCSEs coming up. And I thought I would just go over a sort of revision tactic, but also mental model that will help you master the toughest topics in basically any subject. But obviously, I'm going to focus on physics, and in this example, we're going to be doing electromagnetism. Okay, so what are our anchors going to be? So our anchors for electromagnetism, which is probably one of the toughest, if not the toughest, physics topic. I'd like to hear your opinions on that in the comments below. But because I seem to get a lot of flack on Reddit because I don't seem to make these hard enough. So anchors for electromagnetism, I would say, is the motor effect, the Fleming's left-hand rule, and electromagnetic induction. These are the three principles that underline any question you see in electromagnetism. The benefits of breaking down revision into just three key topics. Also, leave a comment down below of a topic you'd like me to make some anchors for to help you with your revision. If you know these three main topics, you don't need to go into the minutiae of exactly, how does this charge flip and what's hysteresis, all these kind of things. You don't need to go into the weeds. If you know these basic concepts, you're going to pick up most of the marks. Got a little gift there. Is the gift going to work? It's not working. All right, there you go. So it's basically a left-hand rule, okay? So let's discuss the motor effect. So the motor effect is where a current carrying wire in a magnetic field experiences a force. Why is this? Well, if you look at the diagram on the left, we have a orange wire that's running into the screen, and the magnetic field is flowing anti-clockwise. Okay, so it's going around like this. Okay, and then let's say we have a magnetic field, a permanent magnetic field. It's going from north, which is the red, to south on the blue. And so we have these lines coming across there. And then the result of this is if you look at the bottom half of the wire's magnetic field, you can see that the direction of the wire's magnetic field and the permanent magnetic field are in the same direction. So if you think about vector addition, it's like these vectors add up. Okay, so you get a really, really strong field moving in this sort of left to right direction at the bottom of the wire. However, if you look at the top of the wire's magnetic field, we can see that the direction of the wire's magnetic field is going opposite to the direction of the permanent magnetic field, which, as if you have vectors in opposite directions, they cancel out. And so if you follow the arrow, we get into this position. We get into the situation where you have basically no magnetic field at the top, and you have a very strong magnetic field at the bottom. The reasons for why the force is down is slightly difficult to understand, but essentially the presence of the magnetic field at the bottom of the wire actually forces the wire up, but because of Newton's second law, every action has an equal and opposite reaction, the wire moves down in order to compensate this. So that's the observable effect you see. And if you use the left-hand rule, which I'm going to go into a little bit later, we can see that if the current, you do this yourself, get your left hand up, right? I want to see it. Have you got it up? Good. Point your second finger, which is current, into the page. Rotate your finger so that the field is going from left to right, and you should see that the force is going down. So that is the motor effect. You don't need to know the exact reason why this happens, just need to know that it is when a current carrying wire experiences a force in a magnetic field. The left-hand rule. What's a really easy way to remember the left-hand rule? Well, I've labeled it on the right, left pretty well for you. So thumb stands for motion, so that's the force. Field, so F, first finger, that's going to be the magnetic field direction. And your second finger, so C, is going to be current. So, and you can apply this to any question, and if you remember this, you picked up most of the marks. Now we have a very key topic called electromagnetic induction, which is a principle that says there is an induction of an EMF, electromotive force, across a current carrying wire in a changing magnetic field, but also that there is an induced magnetic field across a current carrying wire with when an EMF is across the wire. Okay, so that sounds very, very complicated. Let me break it down. So essentially, the version that I've written on the screen is, let's say you have a magnet or magnetic field, and you have a wire inside the magnetic field. So the magnetic field is generated by a permanent magnet, let's say, and you've just got a current carrying wire, like an EMF induced across it. If it is moving through the magnetic field, okay, the only way you get an EMF induced is when there is a relative motion of the magnetic field lines and the wire. The reason for this is a bit difficult, it's what you learn in A level, but it's to do with the rate of flux, so the rate at which you cut the magnetic field lines, and that's what determines the EMF being induced. And so in this little diagram that I've drawn in the bottom right, I've shown a permanent bar magnet, which is going to have obviously a magnetic field around it, moving through a coil of wire, and that magnetic field is obviously changing throughout the wire, and as it's moving, right? Because you've got this net cutting of the magnetic field lines in the wire, and so as it's moving, you'll actually notice the little dial, which is the voltmeter, tip to positive, but only while you move it. You'll notice that if you stop moving it, if the magnet gets lodged in here and stays stationary, you'll see that there is no EMF induced. And this is why it's so important why I put it in italics, the changing magnetic field, because right now it's stationary. Right now we have a magnetic field just in the wire, but the wire is not connected to any electricity. And so because there's no relative motion, there's no EMF induced across the wire. However, if you start to move the wire in the past the equilibrium point, past middle, you'll see a negative PD being induced. Again, the reason for this is a bit difficult as to why it is negative, but the only thing you really need to know at GCSE is that there is an EMF induced across the current carrying wire if there is relative motion of a magnetic field. So basically, there's a magnetic field cutting the wire. Cool. And the other part of it is actually why this whole thing is called electromagnetic. Okay, so we've basically said from a magnetic field, we can induce electric current, right? Because EMF is electromotive force, which is PD, which is therefore current. But we can take it the other way, right? We can say that if we have an electric field, well, we can also induce magnetism, and that is absolutely correct. In fact, if you heard of the right-hand thumb rule, that's essentially the whole, that's a result of this electromagnetic induction theory. So essentially, if you have a wire that has current passing through it, there's going to be a magnetic field around it. And the direction of this magnetic field is determined by the right-hand thumb rule, where your fingers, so your thumb indicates the direction of current, and your fingers indicate the direction of the magnetic field. Okay, so this should help us with the next few questions. So next question is about two metal rods being placed inside a coil of wire. When a direct current is applied to the coil, a magnetic field forms and the metal rods move apart. Explain why the rods move apart. So we've got to think what's happening here. Okay, so there's a DC current supplied to the coil, which is obviously going to induce a magnetic field as a result of the electromagnetic induction. And so the metal rods themselves are going to assume, because they're in contact with the coil of wire, they're going to assume a magnetic field as well. And so we can say, well, the question says the metal rods move apart, so therefore it must mean that the magnetic charge, charge is kind of a strange way to say it, but I said the polarity of the magnetic fields of the rods must be opposite. So that's what's causing the repulsion. Okay, so we've got to think about what are the processes going on here, what's getting turned into what, or what's causing what. So we have a DC supply here, so you have electricity flowing through the coil of wire. This induces a magnetic field in the coil of wire, which, as a result of being connected to the metal rods, also induces a magnetic field in the metal rods. Again, electromagnetic induction. And the electromagnetic field of the rods they've now assumed must be in opposite polarity, hence the repulsion. Next one. Question. Okay, slightly harder question. This one. This might need a little bit, and this one might need a little bit of contextual knowledge from you guys. But the question is saying, when you switch off current, metal rods return to their starting places, right? So remember, they've repelled, so they've moved up the size of the coil. So they've moved up the size of the coil, and now suddenly they drop back down to their starting places. The reason this happens is because clearly, the question says suggest what material the metal rods are made from. And so let's just think about logically what's happening here. Well, to be repelled in the first place, the metal rods must have been magnetized. But then the fact they just return back to their normal positions must mean they've become demagnetized. So there's a certain class of magnets that can be turned on or off, that the magnetism can be turned on or off, and they're called soft magnets. Okay, so to get your first two marks in this question, you want to state what type of magnet it is and why. So I said it's a soft magnet because the magnetism can be turned on or off. And I've also answered the question. So I've said what material is the metal rods made from. I've said soft iron. You might think, well, where have you got that from? Well, if you do a lot of stuff in solenoids, or if you've paid attention to your sort of transformers lessons, I'm sure your teacher was talking about soft iron core, which actually enhances the magnetic field of a solenoid. Again, that's a topic that we can cover later. But yeah, soft iron is a winner for soft magnet. Okay, and our final question. Is that it? If you have a few more questions. Yes, here we go. The final question is: a direct current in the coil is replaced by an alternating current. Explain what will happen to the magnetic field. Okay, well, let's just look at electromagnetic induction. So the current's moving in one direction, then we're going to have, if you think about get your, I want to see you get your right-hand thumb rule out, basically just form a thumbs up sign. Let's say the current is moving in a certain direction, let's say into the page. Well, the field lines are going to be moving in one certain direction. In this case, it would be clockwise. But then imagine we flip the direction of the current. Oh, now look what's happened to the direction of the magnetic field. Your fingers are wrapping in an anti-clockwise direction. So all that happens is the field is switching polarity, right? Remember, when a field switches polarity, what we mean is the sort of north-southness of it. The thing that determines whether it repels or attracts another magnetic field. So what we say, instead of saying the field switches direction, we say the field switches polarity. Why? Because the field in the coil is alternating with the current. Because of electromagnetic induction, the magnetic field is only caused by the current. So whatever the current does, the magnetic field will follow. So hopefully, guys, this concept of anchoring, of distilling complex topics into just 3 topics, which were, in our case, they were the motor effect of Fleming's left-hand rule, electromagnetic induction. Hopefully this principle allows you to simplify your revision as you get close to the exams, allows you to think through questions very much more clearly. And yeah, I wish you the best of luck. Please let me know if this was too easy, if there's a topic you'd like me to cover that was harder than this. I'm always looking to help you guys out. Remember, I teach also maths and economics as well at GCSE level. So anything related to that, I'd be more than happy to help. All right. But otherwise, best of luck, and I will see you next time. Bye-bye.